Welcome, everyone. Today, we're diving into limited dependent variable models. These models handle situations where the outcome we're studying can only take on a limited set of discrete values. Think about choices like whether someone works or not, or which brand of a product they buy. Understanding these models is key to analyzing decisions that aren't continuous but categorical in nature. Now, let's explore the types of limited dependent variables. Some are binary, meaning they have just two possible outcomes, like working or not working. Others are multinomial, with more than two choices, such as selecting an occupation or a brand. Because these outcomes are discrete, traditional regression methods don't quite fit. Instead, we use specialized approaches tailored for discrete data. When it comes to modeling binary outcomes, there are four main approaches to consider. These include the linear probability model, the logit model, the probit model, and the tobit model. Each offers a different way to estimate the relationship between variables when the dependent variable is limited or discrete. Let's start with the linear probability model, or LPM. Imagine we're looking at whether a family owns a house based on their income. Here, the outcome is either owning a house or not, coded as 1 or 0. Although this looks like a typical regression, because the outcome is binary, the model actually estimates the probability of owning a house given the income level. In this setup, the expected value of our outcome variable, given income, represents the probability that a family owns a house. This works because the binary outcome follows a Bernoulli distribution, where the probability of success is the chance of owning a house. So, the LPM essentially links income to the likelihood of homeownership in a straightforward way. Digging deeper, the Bernoulli distribution means the expected value of our outcome variable equals the probability of the event occurring. So the conditional expectation from our model directly gives us that probability. Also, if we consider multiple independent trials, the number of successes follows a binomial distribution, which has well-known mean and variance properties. Moving on, logit and probit models are the most commonly used for estimating relationships when the dependent variable is binary. Unlike the linear probability model, these models handle the limitations of binary outcomes more effectively. They belong to the family of generalized linear models and rely on maximum likelihood estimation rather than ordinary least squares. To put this in context, a general linear regression relates a dependent variable to several independent variables, with coefficients estimated by ordinary least squares when the outcome is continuous. But when the dependent variable is discrete, like a yes or no choice, logit or probit models become necessary to properly capture the relationship. In these models, the observed binary outcome depends on an underlying latent variable crossing a threshold. If this latent variable exceeds a certain cutoff, the observed outcome is 1. Otherwise, it's 0. This threshold concept helps us understand how the binary outcome relates to the continuous latent process behind it. Specifically, the binary logit model expresses the probability of the outcome being 1 using a logistic function. This probability depends on the explanatory variables through a formula that ensures the predicted probabilities stay between 0 and 1. This is crucial because probabilities outside this range wouldn't make sense. The logit function transforms probabilities into log odds, which can range from negative to positive infinity. This transformation allows us to model the relationship linearly in terms of the log odds, even though the original probabilities are bounded. However, the parameters in this model can't be estimated using ordinary least squares due to this nonlinear relationship. An important concept here is the odds ratio, which compares the odds of an event occurring between different groups. For example, if we're looking at whether a child attends school, the odds ratio tells us how likely it is for children in one category to not attend compared to a reference group. Values less than 1 or greater than 1 indicate lower or higher odds, respectively. Taking the natural logarithm of the odds ratio gives us the logit model, which is linear in parameters and explanatory variables. This semi-logarithmic form is widely used because it simplifies interpretation and estimation. While ordinary least squares can't estimate these parameters, maximum likelihood methods provide consistent estimates.